There we go. So first, thank you very much for inviting me to give this seminar. As I was saying, it's a good opportunity because I won't be going to AGU, so I can still give a talk. And thanks also, Chris, for writing the very nice introduction in the announcement email. So obviously now I have to live up to the expectations. And so today I'm going to talk about the starting phase of an earthquake. So maybe I'm not sure whether to call it nucleation, because nucleation is rather this very slow process before the earthquake itself, or rather talk it the breakout phase where it starts to become dynamic. And so this is what ChatGPT came up with when I asked to draw an earthquake. So just to see that the art generated by ChatGPT is not, in my opinion, as good as the one produced by humans. So if Paul is listening or will listen to this, please go on producing your fantastic paintings, because they're still, your skills are still required. And this is an art, collective artwork that we are doing in our department, painting a giant beach ball with the globe, with a bit of fantasy. I hope my science today would not be too much fantasy. So what's the motivation behind this? Well, part of it were ideas that I had before, and then about a year ago, I was at a workshop and one of the students asked, is there a difference between big and small earthquakes? And then there was a big debate, and we took quite extreme position, Bruce Shaw and myself, and then all that for me to realize that I didn't have really a very solid base to explain why I thought that they could be different or not. And so I started to put everything together in a paper, and this is the result of it. So of course, bigger earthquakes are bigger, so they're different in that sense. But because of self-similarity, we know that they should be exactly this small, bigger version of smaller earthquakes. Is that completely true? I think there's no simple yes or no answer to this question. And related question is, how do earthquakes start? How do they stop? Is the stopping related to the starting? And also, importantly, do small and big earthquake happen on the same faults? And what about the role of fault geometry and fault segmentation? So we're going to go over nucleation observations on both natural faults and in laboratory simulated faults. We're going to revisit some basic concept like Griffith's critical crack. And then we're going to look at a solution for rupture acceleration, a very simple solution based on fundamental principles. And then we're going to take it a notch more towards complexity. So because we all know that nature is much more complex than the simple models we can come up with either in the lab or mathematically. So there's essentially two parts here. One, just to be clear, is the scaling of the breakout process. And I'm going to argue that this scaling, that the breakout process and also the speed of the breakout process scales with the size of nucleation. So that's going to take a new look at Griffith's crack, critical crack, which we recently had, 3 years ago, relatively recently had the 100-year anniversary of Griffith's paper, which was published in 1921. So we're going to revisit that and put it in a more contemporary context and use that to derive a solution for rupture propagation. That's one part, and that's a simple analytical solution that I'm going to show you that reveals some scaling that I think is really interesting. The other part is a bit more speculative, does this have implication on, possible inferences for probabilistic forecasting and early warning? In that case, we have to make inferences about fault structure and how the fault structure can act as a boundary condition on both initiation, propagation, and arrest of rupture. So first, let's go a bit in the literature and see what has been observed on big megathrust faults. So there was this process that lasted up to several months with a slow slip preceding the Chile megathrust events, known also as the Iquique earthquake. And here we have two different papers where the geodetic data has been processed to show that. So on the left is just some paper by Ruiz et al. And on the right, a paper by Soke et al., essentially showing the same thing, maybe a little more stations in the paper by Soke. And it showed with color code. Instead, the other one is showed with error bars and dots. But essentially, the idea is that everything started to move on the fault slowly and culminated in an 8.2 magnitude earthquake. So you may ask, like, okay, these kind of slow events may happen without an earthquake ending sometimes. So the two things may be just related sometimes. This may be part of the nucleation. You may have earthquakes without this process. Yeah, but generally speaking, the idea here is that there's a very big earthquake observed with a very large and long pre-sleep, which can be interpreted as the nucleation phase of the earthquake. This is another interesting one. In this case, the pre-sleep or the slow sleep event was much larger in the area that it occupied with respect to the earthquake. So the earthquake was within the area that started to sleep earlier. So this tells us that there's a complex interaction between slow sleep during the earthquake cycle and eventually dynamic earthquakes. And so if we want to talk about nucleation, we have probably to see how the two interact and how often they are correlated. And this is another example, a much smaller earthquake, 3.5 magnitude in Alaska in the paper by Tape et al., where here there were 4 shocks for a duration of about 12 hours and a very low frequency event that lasted about 22 seconds. So this is a bit very general overview of recent things that have been observed, not exhaustive, but just to tell you what's going on. So the idea also that there may be some difference between big earthquakes and small earthquakes in the way they start seems to be contradicted by this study by Meyer et al., where they looked at, I don't know if, can you see the mouse when I use it on my screen? Yes, okay. So they looked at a number of earthquakes from magnitude 7.5 and 7 and above. And if you look at the initial slope of the moment rate function, it looks like they're all the same. So no difference in the way they start. This is a range of magnitude, which is obviously limited to 1.5 difference. Then there's other studies like the work by Simona, who I think is listening now, where they claim the opposite, that they say, okay, there seems to be, if I describe the moment rate that I derive from seismological data as sort of functions that peaks and then decays again, where I can have 3 types of development here. The first one is they all start the same, okay, and they just grow bigger and then they stop, and this is more very similar to what Meyer et al. Claimed in their findings. Or it can start faster for smaller earthquakes, and then if you observe the initial seconds of the seismogram, you may be able to predict, how far it's going to go. Or it may start slower for smaller rupture, and this case would also be predictive. It turns out that if you do give a characteristic time to the rise of these moment rates and try to model the first seconds of the seismogram with these characteristic times, then you end up, according to Colombelli and et al., you end up having a longer characteristic time for the bigger earthquakes, okay? There are 2 characteristic times. One is the start, one is the reach of the plateau, but let's not go into the details. So here, I think the jury is still out on deciding whether we do observe a difference in the initial acceleration of the moment rate between small and large earthquakes. Just a note that, yeah, in the work by Colombelli, the range of magnitude is a bit more extended. And if you do indeed check the difference between magnitude 7 and 8 or 8.5, it's not very large. So maybe you would start to see that difference if you drop to smaller magnitudes than 7. Okay, so there's also something that made me think a lot, is that there seems to be a very long precursory phase on interplate earthquakes. But on the other hand, it's not that long for intraplate earthquakes. This is the work by Bouchon et al. In 2013. So there's this acceleration, which can be shown in the cumulative seismic moment, which is released, or also in the number of earthquakes before the main event. And this systematic acceleration by stacking many different earthquakes is not observed in intraplate context, or if it's there, it's much shorter in time. So the question is, maybe because intraplate earthquakes are smaller than interplate earthquakes, or maybe they happen on a different subsets of fault or different fault network that have different properties, or maybe a combination of both. So those are all food for thought. Also more recent work where by correcting the apparent energy, by incorporating the fact that there may be overshooting the earthquake rupture, Alice, Gabriel, and al. Showed that there seems to be a different trend between small earthquakes and large earthquakes. Their interpretation is that there's enhanced dynamic weakening in large earthquakes due to pressurization, so that creates this difference. But basically, okay, so this is an indication that maybe small earthquakes and large earthquakes are somewhat not totally identical. Now, okay, let's look at laboratory experiments. So, okay, I'll have to switch to the video here. Hopefully it's going to work. So yeah, so these are experiments that we've been doing first in Rome more than 10 years ago, and now we're doing them here. These part of a work that involves Latour and Alex Shubnell and other colleagues. And this is basically filming with a high-speed camera the nucleation and the breakout phase in a transparent sample in the lab. So this whole event takes a few tens of microseconds, and thanks to the stress concentration that creates this interferometric pattern, you can follow the tips of the rupture, and you actually can. So let's go back to this now. Oh. So you can actually plot the rupture front as a function of time. And what we did observe back about 10 years ago was that you had different developments here. If the nucleation was a little larger, the acceleration was slower. And then for smaller nucleation sizes, it seemed to accelerate faster to reach the dynamic or the limiting velocity in less time. And the way you control the nucleation size is by increasing or decreasing the normal stress. And there seems to be 2 or 3 different phases during the rupture front advancement. So back then we tried to understand what controlled this scaling in the velocity of the rupture front. We did realize that there was a scaling. We were able to collapse basically all the simulations, all the experiments together by dividing the length by the initial length of the nucleation. But we weren't sure about what controlled the timing of how it developed. And it took me basically 10 years to figure this out. And I hope I'm going to show this today to you. So first, a few energy concepts. So it's been about 100 years since Griffith wrote his seminal paper on how cracks become unstable and start to propagate. And it's based basically on his paper. It's essentially three equations. The first one gives the amount of energy that's liberated by forming a crack. The other one is how this energy changes if the crack is extended. And finally, if the energy available is sufficient to overcome the dissipation of the advancement of fracture, then you have an advancement criterion. And he got a limiting stress, which he called R, which is essentially the same if you use these parameters. So TR and C for Griffith are dissipation, which I call in this talk gamma, stress drop, which I call here delta tau, and L, which is the critical length. In that case, then this equation equates to this one, the square root of shear modulus times the dissipation divided by the characteristic length. And then there's a dimensional shape factor, which is dimensionless. And if you arrange this, you get the critical length or the critical Griffith crack, which is in the form which is a little more familiar to us, perhaps, which has been introduced by Joe Andrews and others to explain the propagation of rupture in earthquakes. And the gamma here, the gamma is the energy that's dissipated in the fracture advancement. Part of that could go into the frictional weakening. Part of that could go into the plastic process at the rupture tip, and part of that could be off-fault damage. And so the idea is that when you create a crack, you release elastic energy in the environment, which scales with the size of the crack. And this energy, so if you increase the size of the crack, there'll be more energy available. And if you need energy to produce some new surface, then if this energy is sufficient, then the crack is going to advance. And so we have the energy flow essentially produced by the crack per unit advancement. I call it here G0. It's proportional to the length of the crack times the stress drop square. Now, and that's again the same as Griffith's criterion here. If you replace the values, the symbols by their value, R is the stress, C is L, and then there's a geometrical factor, which is a little different because Griffith was working 2D. Here, I just don't assume any geometry, so I give a general factor. If you go dynamic, what happens is part of the energy goes into waves, and sometimes the waves don't have time to catch up with the rupture tip. They stay behind, so you have less effective energy at the fracture tip to induce the advancement of rupture, and therefore this energy, which is the G0 for the quasi-static case, is modulated by a function which is similar to this, which basically decreases as the rupture velocity accelerates. So VR in these slides is the rupture velocity, and Vlim is the limiting velocity in the subsonic regime, which for in-plane cracks would be the Rayleigh wave velocity, and for anti-plane cracks would be the shear wave velocity. And we're going to look a little bit whether in the general case we can find a limiting velocity which is equivalent to an average of both. So basically, you don't have as much energy if you go very fast. And this problem, let's see if, so there are several things to observe here. The amount that reaches the crack tip, part of it is lost in waves, but this is a solution obtained first for a point, which is the rupture tip. So you have to assume that you can make the balance of all these terms at the rupture tip, and that the dissipation happens in such a small volume that you can assume that it's all located at the rupture tip. So this is a first approximation. The second limitation is that this solution is derived for two-dimensional velocity, so either mode 1 or 2 or 3. And in that case, the limiting velocity is uniquely defined. And finally, this 1 minus VR over V lim is an approximation. In fact, the actual solution is a little more complicated, but if you linearize it and look at the limit at low velocity, you get this. So this is an approximate solution for the propagating crack. This is an example comparing the full solution for an anti-plane crack and the approximation, which is this blue dotted line. So you see they altogether, they don't differ so much. They're both monotonically decreasing with the rupture velocity, and they reach zero when the rupture velocity reaches the limiting velocity, which is the Rayleigh again, or the shear velocity for in-plane and anti-plane cases. And most importantly, if you go to low velocities, they are basically identical. So if we want to look at the breakout phase, it's good news. So how accurate is this approximation? Can we use it for dissipation which is non-local to the rupture tip, but more distributed, like in the case of frictional weakening, especially in the first phase of the rupture propagation, where the front is still extended and not contracted due to Lorentz contraction as later in the propagation? And are we allowed to use that for inhomogeneous conditions in terms of the scaling and the general behavior? So we can check numerically, okay, because this is an analytical solution. So let's find numerically, we can test it and see what are its limitations in the more general cases. But first, let's use this to find a specific solution for the rupture front, okay? So this is the mathematical solution. Again, I'm writing three equations that you already saw. The first one is the static criterion, the static energy flow, which is made available by the formation of a crack of dimension L. The second one is the critical Griffith length for a crack under a dissipation of gamma and a stress drop of delta tau. And the third one is the advancement criterion of Griffith applied to the case when there's waves, where you have this modulating factor here, which is the velocity dependence. So the dissipation has to be matched by the available energy, which is on the right-hand side here, which is the same as the static energy of the crack modulated by this velocity function. Now, the trick I did is I just multiplied the first two equations together and rearranged them, and all the complicated terms like the square of the stress drop, the shear modulus, and the geometrical factor disappear, and you're left only with these very, very simple equations, where the ratio of the dissipation to the static energy flow is equal to the ratio of the critical Griffith length to the current rupture length. So that's an interesting thing, because basically we can now use equation 3 here to replace the value of gamma into equation 4, and we obtain a very, very simple differential equation that gives us the rupture velocity as a function which is just 1 minus the critical length, which is the initial length of the instability, divided by the current length of the rupture. So this is quite interesting. So this is the limiting velocity. This is quite interesting because you immediately see that you have the current length is scaled systematically by the initial length. Basically all the complexity is already included in this single parameter. Now, because we have a differential equation, we can plot the rupture velocity as a function of position, but we can also try to solve this differential equation to find the function L as a function of time. So given that it's simple enough now, it should be easy. So let's first plot this. So this is how it looks. So you start from the critical length, and the velocity then increases. And as the crack lengthens, it tends to the limiting velocity. Everything is normalized here. So the limiting velocity in this case is 1. And the crack length is a function of 1, which is the initial instability length. Good, so this is at least something. Now we can solve this differential equation, and we get something also which is not too complicated. So this is a product log function which has several branches. The first branch is called omega 0, and this is an exponential. And again, here we see that everything scales with the initial length, but we also have here a characteristic time that appears, which is LC over Velim, which is the limiting velocity of the crack. So there's a double scaling here, spatially it's LC and temporally it's LC over Velim. So in the limit of large times, this part here, which is a bit more complicated, simplifies, and you have just a linear dependence, saying that basically the crack is propagating at the limiting speed. So again, we can plot that, and this is how it looks like. So this time on the horizontal axis is time, and on the vertical axis is the length of the crack. Here I'm assuming it's bilateral, so it accelerates and then reaches some kind of constant velocity. Obviously, then it could transition to super shear, which I'm not considering in this work because I'm interested in the breakout phase where the rupture is still relatively slow. Okay, so the same solution. We have, again, a self-similar solution. It's rescaled in LC in space and LC over Velim in time, which means the duration of rupture acceleration is proportional to the initial breakout length, which simply translates into a larger breakout will start more slowly. So if you have a very big nucleation patch that starts to accelerate, it will be more slow than a small patch that will start to accelerate and cause an earthquake. So because this is derived for a very simple case, how can we generalize this? How accurate is it? How can we translate it in 3D? And how can it translate in complex case with inhomogeneous distribution of parameters? How does it compare to lab experiments? And most of all, can we use it for real earthquakes? So here I have to stop for a second and say a very nice sentence by Poincaré, which used to say, simple models are wrong, but complicated models are useless. So we sort of have to find a compromise. My hope is that simple solutions still could give an insight into problems which can be more complex, in special case for the scaling, and we can still use it. So let's go to the movies again now and see. So the second movie is a 2D simulation that I did, very simple, basic finite difference of dynamic rupture. It was a bit challenging to very close to the instability because I'm looking at the acceleration of rupture in the initial instance. So if I overload the rupture, it's going to accelerate too fast. If I underload it, it's going to stop there and not propagate. So there are several tricks that you can use. One trick is to add one rupture at a time until it propagates, but that's a sort of quantized approach. So you can overshoot very easily the ideal solution. The other way to go around this is to increase the load very gradually on a crack which is of prescribed length until it propagates. And here I show the stress concentration and the way the rupture tips start to propagate and accelerate. And this, I solved it for a homogeneous model. Then I did something similar in 3D, which is a bit more challenging in terms of getting really close to the unstable initial limit of the rupture. And just for fun, I added some relatively strong inhomogeneity to the pre-stress on the fault. And instead of using a simple elliptical or circular shape, I just used a random initial like flower-like structure and see where it goes from there. And so you see that rupture starts to accelerate. It kind of eats in the regions where the pre-stress is a little higher and accelerates a little more. It tries several times to, now it stopped, okay. It tries several times to switch to super shear in different points of the rupture front. Okay, now it's moving again and it fails, but then finally at the very last snapshot, it starts to develop the typical super shear features on the left and right, and you have this transition, okay? So these are the numerical solutions. So I think I'm done with the little movies now. And so the question is, in 3D, we want to scale everything by typical length. So what's the typical length for a crack that has a non-trivial shape in 3D? Well, we can use the square root of the area to define a typical length. And if we take the square root of the area divided by pi, it corresponds to the case of an ellipse, where you take basically the average of the small axis and the large axis of the ellipse. But it's not just any type of average. It's called the geometrical mean, and it's the square root of two quantities multiplied together. So this would give the typical length of an ellipse. And more generally, if you just take the area of any shape and divide it by pi and take the square root, it would give a characteristic length. So how does that work? We'll see. The other thing we need to define in 3D is what's the limiting velocity. We know that in plane is Rayleigh wave, antiplane is shear wave. Well, let's take the same approximation, because one front will be faster than the other. If we assume that the rupture can be compared somehow to an ellipse, which is often the case, then we take the square root of the two velocities, and we got this geometrical mean again, and we define this as the limiting velocity, which basically you have a single length now and a single velocity, which is a sort of average. Now you see how I always tend to like to go to simple solution. I lost one of the graphics in the process here, but no, not a big problem. Here is the comparison for the 2D homogeneous solution. So I did three different things here. First, I plotted the analytic solution, which we derived just a few slides ago. And then I plotted the numerical simulation for an initial length of, well, it just happens to be 609 meters if you want to put a dimension, and then twice as much, which is 1218 meters. And I normalized the numerical solutions and verified that they plot exactly onto each other. So the scaling is definitely preserved in spite of the solution being a little more complicated than the simplified one that I derived. And they both match pretty well the analytical solution with minor differences. Then this is the 3D solution for the inhomogeneous fault. So I did the same thing. So the rescale problem overlaps. So the scaling is respected although we are in 3D. And again, the analytical solution is pretty close, except that the numerical one tends to accelerate a little faster because it eats into the high pre-stress regions and wants to transition to super shear.
Stefan, sorry, Massimo, just a clarification. But do you still have a limiting velocity in 3D? And should this limiting velocity be smaller than S-wave velocity?
No, so the limiting velocity in the subsonic regime is an equivalent velocity in 3D, and my interpretation of that, but actually I would really like to show the third graphic, which I lost here, because it's the 3D homogeneous case, and the match between the analytical solution and the numerical one is almost perfect, which I'm saying this to sort of justify my choice of taking this definition of limiting velocity. So again, if you have an elliptical shape, which the major axis of the ellipse would be the shear wave times time, and the minor axis would be Rayleigh times time, then this will be the correct value for an average velocity of the rupture front. Okay, so that's my interpretation. Obviously, in real life, you always end up having a super shear transition, and this doesn't work anymore. But given that we're looking at the breakout phase today, I assume that the super shear transition happens sometimes later along the line.
Yeah, because my question is mostly derived by the fact that in 3D, I would consider the S-wave velocity as the real limit without a big separation, but with your expression, yes, you should stay well below.
Yes, on average, if I define the average velocity of the rupture front, it will be a little slower than the shear wave velocity.
Okay, thanks.
You're welcome. Okay, so how does it match the experiment? So finally, I go back to our work with Latour about 10 years ago. And indeed, if I use this solution here, I find that there's a linear dependence between the velocity at any given distance from the initial position of the rupture, which is shown by, okay, these dots. So the dots, the orange dots are actual measured velocities during the experiment, and the blue dots are inferred velocities. Inferred, so sorry, scratch that. The orange dots are measured lengths of the initial unstable asperity or critical length, and the blue dots are inferred using the same normal stress dependence as the orange dots. But they seem all to align pretty well along a linear trend, which, if you find the best fit, is giving a limiting velocity of about around 1400 meters per second, which is what we expect in the plastic material that we use. And the sensor at which these velocities were measured is about 3.7 centimeters away from the initial rupture front, from the initial tip of the critical crack. So it seems to work to explain how this contraction of the acceleration happens for smaller cracks and bigger cracks. Okay, so okay, now I've been discussing about energy criteria up to now, but what I'd really like to stress here is that whether you want to use the Griffith crack with an energy criterion, or whether you want to use the critical length derived from rate and state friction laws, and first defined maybe by Rice and Wiener, and in its different realizations after that, these problems are somehow equivalent. So in terms of rate and state, you have, I wrote here 3 different critical lengths. The first one is the classic one that you may be used to see. The second one is the LB, and the third one, most importantly, is L infinity, which was defined, I believe, by Rubin and Ampuero, which applies when the rupture is advancing, because there's a very sudden change in the state variable, so you're very far off the steady state, and in that case, the critical length is equal to this, which is a little more complicated. Now, I just want to make a parenthesis here. There are, in my opinion, 2 different things. One is instability within a patch that does not necessarily create rupture propagation, but you just may have accelerated sliding within a patch of dimension LRR, and then it would just die out without inducing any earthquake or any rupture propagation. And in another case, you do have instead an instability patch that starts to expand, and that's rupture propagation. So either this case, I believe, would be described by either LRR or LC or L infinity. Okay?
Stefan,
So yes?
Sorry to interrupt. Can you go back 1 slide? This might be too complicated now, but just like to make a question that we can follow up on later about the possible difference between LR, what you call LRR, and the LC or L infinity here. Because in your model, one of them, your model, when it first starts out and the velocities are very low, then you don't have this issue that's part of the Rubin and Ampuero term of sudden acceleration, because you really are close to steady state.
Yes, right. I don't. So in the models that I show, the numerical models, I don't implement rate and state. I just go directly for a simple slip weakening law. So obviously that makes it more challenging to be close to steady state when you start. But yes, it would be interesting. That's one of the things that would be interesting to do, is to combine both the enhanced dynamic weakening and rate and state laws and see how the acceleration works in that case. I think that would provide a more complete model. So the point here was that I believe that both lengths, like the critical crack by Griffith or L infinity in this case, which is the rate and state equivalent for propagation or rupture, in my opinion, are equivalent. And I think this has been showed also by Rubin and Ampuero, where you look at the friction curve after a velocity step. And in case the step is big enough and you're far from the steady state, which you imagine would be the case for propagating rupture, then the friction decay is almost linear, and the stress drop would be proportional to sigma times B minus A. And the restrengthening would be proportional to A times sigma. The normal stress is sigma. And there's a characteristic distance dc. And if you assume that all the dissipation comes from the friction here, this area here, which is in pink, is proportional to dc and to b times sigma. And therefore, the stress drop square is equal to sigma square times b minus a square. And the dissipation is equal to dc times b. Okay, oh, sorry, sigma times dc times b. So in this case, you can simplify once with sigma, and you have no sigma terms at the denominator. But basically, this expression and for LC, which is based on energy consideration, and this one, which is based on the rate and state laws, in my opinion, are perfectly equivalent. Although the friction law may not be the same, because as soon as you hit the dynamic regime, you may have enhanced weakening taking place. And all sorts of interesting things may happen if you consider that, because if the quasi-static instability patch is smaller than the one, is larger, sorry, than the one given by the enhanced dynamic weakening, then you may have a very large region sliding, which ends up concentrating a smaller rupture patch in its middle. And so that may correspond to an extended slow slip event observed, for example, in Valparaiso, which was followed by a smaller rupture inside.
Stefan, sorry,
please.
this is again Massimo. But if I am a bit lost in your jumping to rate state, because in rate state, L parameter of rate state does not correspond one-to-one to D sub C of slip weakening.
No, it's true.
And there is a stress drop in the middle.
Yeah, I dropped a step here. The DC here is not the characteristic length of rate and state. You have to recompute an equivalent DC. It's explained in the Rubin and Ampuero paper. So this DC is different from the rate and state DC. It's an equivalent DC that comes out when you assume that you're off the steady state. So I didn't want to go into the details of that.
Okay, thanks.
Is that the question you had, Massimo?
Partially, but yes, go ahead. Don't worry about me.
Anyways, so this is just a parenthesis. So in the case is the opposite. We may have an L infinity, which is much smaller and starts to propagate at reduced velocity until you reach the dynamic regime here with the enhanced weakening, and then you get an earthquake. So you have both a larger nucleation area with a smaller dynamic rupture inside, or a small nucleation area which expands it and then accelerates. And both, more or less, you can argue, have been observed in a couple of large natural earthquakes. Now, okay, let's do a bit of dimensional analysis now. And if I take again my critical crack length or my rate and state L infinity, I have a dimension here, which is a length. And if I take the inverse of this length, I define a parameter which I call psi, and I can assume that all the complexity, all that matters for the rupture, all the values that these combined parameters will produce in psi only matter insofar as they are built up together in this combined inverse length parameter. In terms of the rupture propagation, now, if I use this parameter instead of the LC, I will have the product of chi with the length of a potential slip patch, P. And if the product of these two values is larger than 1, then I will induce rupture propagation. If it's smaller than 1, the rupture will abort, okay? So this is, again, exactly the same criterion as LC greater, a patch having a greater length than this. But I find it, for reasons that I hope will become clear in the next slides, preferred to write it as in this dimensional form here, which allows me to derive a parameter which I call now zeta, which is a dimensionless parameter, which is the product of chi and L. So if any region, if any patch on my fault of dimension L has a product of L and chi, which is larger than 1, this, from the energy point of view, is a potential instability and rupture propagation patch. So in this case, it's not only the LC I'm looking at, but the combined length of the patch and the value of the parameters which are inside the patch, which define 1 over LC. So the reason I do that is, okay, so first let me step back a little bit. We saw that smaller nucleations are faster, accelerating faster than bigger nucleations when they go to the breakout phase. The second idea I'm trying to introduce here is that the nucleation size is limited by the fault size, if there's anything we can define as the fault size. Say, let's imagine that the faults are, for a moment, let's take again, maybe an oversimplified model, but let's imagine that fault networks are constituted by separated segments, and you're trying to induce the nucleation on one of these segments. In any case, the nucleation cannot be larger than the maximum size of the segment. All right, first observation. Second observation, if my fault is bigger, which is the case on the right-hand side, then I may have a higher probability of finding a patch which is a bit more overstressed maybe, which is likely to fail because I had just more space to develop a larger nuclease, okay? So in conclusion, automatically, just because of the limiting size, you can't have a big nucleation on a small fault segment. Meaning that statistically, if you have a large fault, statistically, you are bound to observe, on average, larger nucleations on it, because you'll be drawing random sizes, which can be either small or large, whereas on a small fault, you're always limited to a small size. So that's a kind of quantitative argument. Let me try to make now a quantitative statement out of it. So we've seen that we can define a patch with a length and a chi value inside, and call zeta the combination, the factor of both. And if zeta is larger than 1, this will propagate. So if I have a big fault, I'm going to assume that, now make another assumption that big earthquakes happen on systems where the faults are relatively mature because they're plate boundaries and they have been sliding for hundreds of kilometers. And so you get relatively smoother and bigger segments, whereas small earthquakes happen on faults which are more segmented and are constituted by smaller segments. Therefore, the potential breakout patches will be larger on average on large fault segments than small fault segments. And because to some extent the size of the fault segment may limit the final magnitude of the earthquake, well, then there may be statistically a correlation between the initial size of the patch and the final size of the earthquake. Obviously, that is assuming a lot of things, among others, that the segmentation of fault as a barrier and as a magnitude defining barrier for the final size of the earthquake. now we can cite the work by Wisniewski in support of that hypothesis, where you see that the segments that are more than 5 kilometers apart seem to be always stopping ruptures, at least in the small catalog that Wisniewski has been looking at. Obviously, this is based on faults which intersect the surface, and he only looked, I think, at a few tens of events. So, but it sort of indicates that, yes, segmentation of faults is sort of predicting to some extent the endpoints of ruptures. So the next step is, okay, so I created a fault with an inhomogeneous distribution of the values of zeta, sorry, the values of chi, and then I asked the question whether any subset of these faults with this heterogeneous distribution would be likely to fail or not, and whether this had a dependence on the final fault size. So we know that faults are rough, and that their roughness can be described as a self-affine distribution. Such distribution with surfaces in elastic contact will reflect into the normal stress, and the normal stress will reflect onto the friction through Coulomb's law, and the friction will reflect onto the stress drop. So the idea is, if the fault roughness is self-affine, I'm going to assume that my stress drop is also self-affine distribution. And the self-affine distributions are a bit complicated. There are different ways of defining them. You can use either the Hausdorff or the Hurst exponent, or the exponent of a power law. But by taking essentially the roughness observed on a normal fault and translating that into stress distribution, I was able to create this inhomogeneous stress distribution just by taking the Fourier transform and filtering the wave numbers by a power. Okay, so I won't go into more details about this, just to let you know that I created this rough distribution where you have heterogeneities of all sizes, and it's a bit rougher on the small scale, and you have bigger features which are less strong at the larger scale because it is a self-affine distribution. Now, again, the criterion is that the value of zeta is bigger than 1 on any of the patches within this fault. So this is then what I did. I made 5 different faults of sizes 1024, 2048, and so on and so forth, up to 16,000. So if it is helpful for you to think in dimensional terms, you may assume these are meters. So the biggest fault is 16 kilometers, the smallest one is just 1 kilometer. And then I took each of these faults and divided them by 2, by 4, by 8, up to 32 for the smallest one, and up to 512 for the biggest fault. So this is a representation of what I did. So first I divide the fault L by 2 by taking this red line and creating 4 subfaults. Then I divided again by 2 with the orange line and created 16 subfaults, and then by the blue dotted line and created 32 subfaults, and so on and so forth. So then I repeated the whole process 6 times, and every time I asked the question, within these subsectors of the fault, I'm going to look at the value of zeta and see if it's bigger than 1 or not. And I'm going to draw out the value that is the biggest in all the cases. So the value with the biggest zeta is the value that is more likely to fail from the energy point of view. So a combination of high stress and larger failure patch, okay? And I plotted those values for each of the 5 dimensions of the fault, and this is what I get. So the top picture here, so this is a fault of 1,000 meters. The top one is the fault of 16 kilometers. And for each subdivision of the fault, I plot the maximum value of zeta, and I see that the maximum value seems to scale with the maximum size of the fault. There's some variability here, which is shown across the 6 realization of the model that I did. And then if I take the maximum values for all 5 dimensions of the fault and plot it here, this is what I get, a nice log linear trend where the size of the critical patch does seem to increase with the size of the final fault, okay? And the duration is both linear and log linear, and the slope in this case is about, tells you that the size of the critical nucleation should be about 0.2 the length of the final fault. Okay, so this is a very specific example with a specific stress distribution, lots of assumptions, but there seems to be a case for a statistical correlation between the unstable patch and the final and the available space that the patch has is allowed to extend onto. So obviously, bigger fault, you're allowed to select a bigger patch, and because a bigger patch is inherently weaker than a smaller patch, then statistically you're going to observe bigger patches on bigger faults. Okay, so that's the idea. Now, okay, so I went already through this. So if you believe that there's this correlation, then there's a case to make about, observing slower nucleation phases and bigger breakout phases on large faults that are susceptible to generate larger earthquakes than on smaller faults, which are more segmented and which may correspond to the case of intraplate faults versus interplate faults. So now let's go back to seismology a little bit. So you know that the far field is of a seismogram. The displacement of the particles is proportional to the moment rate released at the source, with a number of modulating coefficients here, which belong to the radiation pattern, the attenuation, the distance, and the geometrical decay of the waves and everything like this. But for a given set of these parameters, you do have a moment rate proportionality between the particle displacement and the moment rate. Now, if I take my solution for the length of my crack, which we've seen seems to fit both the in-plane, antiplane, homogeneous, heterogeneous 2D and 3D cases, quite universal, although it's approximate. We're very happy about this. So let's use this and into the expression of the moment rate and get this here and then replace the solution L and square and L dot in the moment rate. And that's what we get. And if I plot it, I get these curves, which I plotted for 3 different sizes. Now let me see. So the smallest one is 100 meters nucleation patch. The intermediate one is 500 meters, and the largest one is 3,000 meters. And so the radiation that you would see in the far field due to this changing moment rate, you see that it starts lower for a smaller fault, but it accelerates faster, okay? So in theory, you could, by reconstructing the moment rate from the far field, you could reconstruct the size of the patch that is undergoing the breakout at that moment. And now, so this is reminiscent a bit of the early warning work that Colombelli et al. Did, where they seem to have different characteristic times depending on the final magnitude. Now, whether this is related to the final magnitude or not, of course, is up, for debate, and depends on, whether I'm making this model somehow realistic or not. And obviously, it's going to depend on whatever observations we can make in the near future with the ever-increasing catalog of earthquakes. Okay, so just for fun, I took these 2 events, which were the Alaska earthquake of 3.5 and the Chile earthquake of 8.1. And I said, if my model is somehow correct, then the scaling of the final fault size, which is for a magnitude 3.5, would be about 500 meters to the time should be the same. So if I take these 2 faults, so in the case of the Chile Iquique earthquake, the indicative fault size is 150 kilometers, and the duration of the preliminary phase here was several months, which translates into about 4,000 hours. And if I take the ratios of the two lengths and the ratio of the two times, I get something which is of the same order of magnitude. So bingo. Of course, you're going to shout at me for, proving a model just with two events in the catalog. But it's just to show the idea that, okay, the duration of the breakout phase or the nucleation size should scale somehow with the final size of the fault, which controls the magnitude. So in this case, I cheated a little bit because I just used one example. And I think, okay, I think that's all. And yes, I've been a little over 1 hour, I guess, but thanks for your attention. And again, this is a ChatGPT generated interpretation of an earthquake.
I like the fact that you're lounging here and in your very first slide. Beautiful talk, Stefan. I will invite people to unmute and join me in thanking Stefan for a great talk. Really, really.
Thank you.
Yeah. Okay, so let's change into an interactive style, and people can probably most usefully. I hear someone's background noise.
Chris, it is a bit noisy, Steve. It's hard to follow.
Okay, all right, I don't hear it anymore. Maybe we've heard it and I got rid of it. Okay, thank you very much. Thank you very much, Stefan. Let's move into an interactive phase, and the easiest way to do it is to use that raise hand feature at the bottom of your screen. Yeah, and so please, I will invite everyone to join us. I will turn off the recording to make it